All right, so today we're talking about operating systems. All right, there are three main operating systems in use. They're kind of general purpose operating systems that are in use. One is, of course, Windows, Mac OS, and Linux. Specifically, a lot of people use Ubuntu for general purposes. However, I personally, I do a lot of security research. So I use Kali Linux or Kali Linux. I also use Debian, which is the foundation of Ubuntu. So I use several different operating systems. Even more so than those three operating systems, we also have iOS, right? That's an operating system. Android is an operating system. So today we're going to learn how those operating systems work. How do they make modern computers functional, right? And possible. All right, so what is an operating system? Again, it's kind of that intermediary layer between what we do and the hardware. So how is it that we have physical hardware that works off electrical impulses that we can actually control? I can touch, you can't see this because the background, I can touch it with a pen and write on a screen. How is that possible? How is it possible that we are able to communicate with one another near instantaneously? Right? Our operating systems are responsible for translating those electrical impulses into computerized signals that we can modify, edit, do all kinds of different things with. So the operating system is an incredible piece of software. That's all it is. I don't know if you all are aware or have been, heard, but Windows, there's like a new computer virus for Windows every other week, right? And something about Windows is getting exploited. Matter of fact, Windows 7, if any of you all remember that, not Windows 7, Windows Vista. Right? I don't know if you all remember Windows Vista, but literally the week they released it, somebody hacked it. It was like millions of devices. And they scrapped it and came out with Windows 7 within like 6 months. Okay. Again, operating systems are just computer programs. Somebody programmed them, such as yourselves, and somebody started where you all are starting and programmed those operating systems. Again, it is at this time where I will start booting people for not having your cameras on. So please turn your cameras on or you will get booted unless you send me an email or something. All right. Okay. So again, operating systems exploit the hardware. They're capable of doing all those things that we use today. It's funny how much we take for granted. Somebody sat down hour after hour, day after day, and programmed these complex software systems that we use every day. Actually, we just throw them out every day. This little pen that I use as my little whiteboard most likely has more processing power than the first rocket to the moon. All right. So the advances we've made in computing and electronics is actually an incredible feat that we take for granted, particularly because we use them every day. And especially because we have so many different devices. We have cell phones, smartwatches, we have headphones, Bluetooth headphones, we have all kinds of different devices that we connect to our computers. So they're actually incredible machines, incredible pieces of software that we use every day. So I'm going to skip through these slides. I kind of talked about all of this stuff. So what is the hardware required? I kind of talked about some of that hardware before in last class, the CPU, memory, IO modules, the system bus. I talked about all that stuff. So again, this slideshow shouldn't take long at all because we covered most of this. However, I do want to show you an example of memory. So here's a quick um, image, quick diagram of how memory and the CPU communicate. So we have computers now, and you've heard of multiprocessors. Okay. So previously, before yours and my time, computers were single processor. Okay. There was one chip per computer, meaning you could only do one thing at a time. You couldn't run Zoom, PowerPoint. I got Microsoft Word open, I got Mail open, I got Chrome open, I got File Explorer open. You couldn't do all that stuff at the same time. It's one or the other. So, although I don't think they're single processor, they may be, but if you use like a Roku or something, you can only open one app at a time. Matter of fact, a couple of years ago, the iPhone, you can only open one app at a time. Having multiple apps open was like, oh, this is a big thing. This is new. Having multiple apps open at the same time, like literally half the screen is this app and the other half is that app, was like huge. It just wasn't there before. You couldn't do it before. Now you can. So we talked about the processor. It's pretty much the brains of the computer. I'm not going to go deep into this again. We've talked about it unless you all just feel like you want to hear it again. Main memory. So again, your main memory is important because it's where all of your programs go when you're running them. So for example, I do a lot of research. Right? So my computer has 32 gigs of memory. And so I'm capable, I have enough memory to run PowerPoint. I actually have 2 instances of PowerPoint open. I have Zoom open. I have Word, Mail, Chrome, File Explorer open. Your main memory, when you talk about your computer running slow, it's typically because you're running out of main memory. So people say, hey, I just bought this computer last year. What the hell is going on? Why is it so slow? Well, the issue is typically computer programs and operating systems get more powerful, require more hardware to run. However, our hardware stays stagnant. If you have 4 gigs of memory, that's pretty much what you got. Now, you can't really update it, especially for laptops. It's kind of difficult. Some let you, some don't. But for the most part, you're stuck, right? Same with your processor. Your processor, you cannot change your processor in the laptop. So once the operating system has used up all the resources available, it's going to be slow. So when people were saying, Apple come out with a new iOS and slows down my phone, it was fine before. Some of that was, I think, actually Apple doing it intentionally, but some of it is due to the operating system being bigger, if you will. They're adding more features. They're adding all these features, and each new feature requires more hardware. Okay. So if you ever wonder why your computer or your phone or whatever is slowing down over time, it's not necessarily strictly because the company is throttling your device. It can be just you're running out of physical hardware. So your IO modules, these are your peripheral devices, communication equipment, so your networking. The data comes from those devices to your computer. Your computer interprets it and communicates that way. All right. So they're actually fairly complex. And the fact that we can do all these different things with computers, again, is truly amazing. All right, gentlemen. Again, if I don't see your face, you will get booted. We only have 2 more classes like this online. Please bear with me and try to follow the rules. So if I don't see your face the next couple minutes, I'm just going to boot you. If you don't want to be here, I'm not holding you. All right. System bus is responsible for moving all of that data throughout your computer. You got your processors. The system on chip is something else. So with a physical big, desktop computer, you can actually swap out different components. You can take out the CPU and replace it. You can take out the memory, replace it. You can do all these, change the motherboard. With laptops, cell phones, Raspberry Pis, there's something called system on chip, where the actual chip is soldered onto the device. There is no replacing it. It is a part of the device. You try to replace the chip, you might as well replace the whole device. That's why you can't upgrade or update a cell phone. The components are just too small. It's not feasible, if you will. So here's an example of this system on chip. This is a Raspberry Pi, by the way. If you don't know what a Raspberry Pi is, it's a small, this is really small. It's like the size of a credit card, mini computer. With the Raspberry Pi, you can create, and the skills that I'm going to teach you in this class, you could create a kind of like contraption, if you will, that turns on the lights in your bedroom when you walk in. It's actually really simple with a Raspberry Pi. You buy a sensor, you buy a light bulb. You plug it in, you write the little program. Every time that sensor, the little infrared sensor is broken, that means you entered the room, turn on the light. Right? After 30 minutes, turn the lights off. You're going to have the skills to do that. So what I'm getting at with all of this is the things that we use every day that maybe, oh, there's no way I could make that. You know, somebody already made that. It's crazy. It works. It's, you know, magic, if you will. No, it's just a programmer who has the skills to make it, which you all will have, hopefully, if you pass this class. So that's the chip right there. Versus a desktop motherboard. This is an example of a desktop motherboard. The chip goes right there. You flick that little thing open, pop the chip in, close it back. You can upgrade your chip over time if you want. Your memory also goes right here. So again, you can pop the memory out and put in some more. Your graphics card goes into these slots. These are PCIe slots. Nowadays, we have something called NVRAM, which is like a really small but super fast solid state drive. That'll go, I think, right here. So there's different things you can do if you are interested in computing and electronics, and which I'm assuming you are if you're in this class. If you're not, I don't know what to tell you. All right, so memory hierarchy, we talked about this last time. So again, I'm not going to go into this too much. But again, we have cache is the fastest. Actually, the registers are the fastest, but we're not going to talk about cache is essentially the fastest. Then you have your main memory or your RAM, random access memory. And then you have your storage devices, which are your SSDs and your hard drives. These are just some considerations for the different types. The faster, the greater the cost is per bit, right? Greater the capacity, typically the smaller cost per bit. But the greater the capacity is usually slower access time. And here's the memory hierarchy. So you have inboard memory, which is your registers, your cache, and your main memory. Outboard storage, so your solid state. So these are actually pretty old technologies, even for you all. Magnetic disk, I don't really know if we still use those. CD-ROMs and CDs, DVDs, Blu-ray. So those are kind of old. We use mainly now flash drives, USB drives, hard drives, solid state drives. So I might need to update this figure. I talked about these memory. I'm just going to show you this diagram. So basically what your CPU does, it manages all your memory. It takes your program. So when you start a program, and I'm going to show you this, I'm just going to draw this real quick. So you have a program, right? You have your CPU. Of course, now my pen is dead. Oh, here we go. All right. So you have a CPU. This is your little CPU chip. All right. Then you have cache memory. So cache. Don't talk about my handwriting. You have cache memory. Then you have your main memory or your RAM. Then you have your storage, right? Either a hard drive or a solid state drive, SSD. Okay. So your CPU is responsible for managing the data between these different devices. Again, this is cheaper. Cache is more expensive. Is it 2 lines or 1 line? I don't know. All right. RAM is kind of in the middle between the two. Hard drives, solid state drives are the cheapest in terms of cost per bit. All right. So what happens is, let's say I have, when you install a program, all you're doing is storing it in your storage device, right? I have Word, Chrome. I have, let's see, PowerPoint. I have that all in my hard drive. I installed those programs. So when I start up Word, what happens is the CPU then takes this data here and tries to put as much of it as it can into RAM. All right. That way it's faster. It moves faster. I click on something, it moves fast, right? I can run the program a lot faster. I'm running Chrome as well. So it's going to take as much of that as it can and puts it into RAM. Same with PowerPoint, right? It's going to take as much, put it in here. However, now you see I'm running out of space, theoretically, right? So let's say I tried to run, I don't know, Call of Duty, right? I tried to play some Call of Duty. I have all these other programs running. What's going to happen is it's going to have to swap between these two areas over and over again. And so it's going to run very slow. It's going to keep going back and forth. My pen stops working. It's going to keep going back and forth and run really slow. All right. And as you're using the individual programs themselves, right, it's going to swap them between cache and RAM. And that just speeds it up. All of these are in an effort to speed up your computer. Right? Speed up your execution processes of your computer. All right. Any questions about that process? Now, obviously, it's a lot more complex than that. There's a lot of different algorithms that play, but that's kind of the gist, the very, very high level of things. If any of you take operating systems, you'll learn more about this. Paging, segmentation, first in, first out, least recently used, all that different stuff. But in this class, I'm just giving you a high level overview. All right. Okay. So let's finish this off and then I'll let y'all out. So I talked about multi-core processors. Again, previously we were using single cores. Now we use multiple cores. So if you hear things like dual core, there's 2. Quad core is 4. Octa, I believe that's 8. A deca might be 10 or 12, one of the two. So we're getting up there now. I've seen one with 24 cores on it, right? And those are typically servers. Just more efficient. I told you last time about Moore's law, which said the number of transistors on the processor would double every 2 years, essentially making computers twice as fast every, was it 2? Yeah, I think it's 2 years. It might be 5 years. However, that law is becoming more difficult because transistors can only get so small. Physically, we're running into that kind of restraint, right? Now it's more about how many cores can we put on an individual chip per computer. Make it faster. You can run more programs at the same time. Even within those programs, there's something called multi-threading, which allows you to run multiple threads at the same time. So if any of you are gamers or you play video games of any kind, right? So I used to play 2K. In 2K, I'm just imagining this. When I used to play My Player. So during My Player on the games, you would have multiple threads or a thread running for each additional player that was on the court with you. So the other team's players had their own individual threads. They were doing their own thing. Same with the other your teammates. They had their own threads. The referees had threads. Basically, what a thread is allows you to run your code individually, right? Isolated from the other ones. Essentially, they're their own little programs. They have their own little artificial intelligence engines, and they're running independent of one another. So multi-threading within the same program. Now, again, 2K is one program, but it has multiple threads running within it. That's what's the beauty of multiple cores. You can run those multiple threads concurrently or at the same time. And in this class, so that's it for that slide, but in this class, you'll hear a lot of terms that I talk about in terms of tech. So concurrency, multi-threading, multiprocessors. Those are just little keywords, buzzwords that you'll hear over and over again as you go deeper into tech. All right. And as we start programming, you'll hear more and more of them. All right. So like I said, that slideshow was